moment, Dr. Becker, we are recording the presentation. Once it's done, the editing, I will share it with you so you can share it as well with your students.
Okay, perfect.
Okay, thank you very much, Dr. Becker. So thank you very much, guys. Thanks for coming. Everyone online, thanks so much for being with us this morning. Today on the 17th International Seminar Series, we have Dr. Becker from the UC Berkeley in the United States. And she's going to talk about seismic isolation and achieving our desired performance goals. Dr. Becker, the room is yours, and thank you very much.
Well, thank you very much for having me. I'm excited to talk to people from a different continent about some sort of shared interests and interest in increasing the performance of our structures under seismic events. So today we'll focus on the seismic isolation, and the question is really, why we want to do this. So we think about our current design codes, and we think about these levels of earthquakes. So we can have these very small earthquakes over on the service level event side that happen quite frequently, and they're not going to cause as much damage. And then we have these beyond maximum considered events, the very large earthquake size. We will never see these in our lifetime where we live, and we don't actually know how big they can necessarily be. So the design codes in general split the difference, and they design for something that's sort of in the middle, and their goal is to protect from loss of life. So if you follow modern design codes, you're going to do a pretty good job saving people's lives. And to do this, we try to stay far enough away from collapse. So we try to achieve low probabilities of collapse. But here is one of my favorite buildings to look at, and it is a building that has not collapsed, although it's pretty close. And what's happened here is this is a mixed-use building. There's houses on top, on the top 2 floors, and a restaurant on the bottom. And so the people who lived on top can no longer live in their building. They have to move away. The people who were making a living, making money on the bottom, they now have no source of income. And this is a huge problem once you get out to not just a building, a block, a city scale. If this is happening all around your city, this can be devastating for not just the individual people, but the community as a whole. So we want to think about how we can design even better than just thinking prescriptively about one event, even though it still is most important to protect from loss of lives. So maybe we think the building on the previous page, it just needed to be stronger. We just needed to design that building a little bit stronger and everything would be fine. So this is a picture of downtown Sendai after the 2011 Tohoku earthquake. And Sendai was the closest metropolitan region to the epicenter of that earthquake. So if you look at this picture, you see that these buildings, they performed very well. I don't see major damage throughout the city. Everything looks fairly normal. But this is from one of my colleagues inside their offices at Tohoku University. And so you can see, even though the structures themselves seem to be strong, seem to not have damage, those strong buildings, very stiff, cause high accelerations, and the damage is caused interiorly to the non-structural components. So we have to think about both sides of the picture, protecting the building and protecting the non-structural components, because as you can see, if these are not braced properly, if my non-structural components are not designed properly, these can cause loss of life, injuries, significant downtime, and damage. So imagine if this was a chemical processing plant, if this was a laboratory. I mean, in terms of amount of loss of days at work and in terms of loss of productivity, you're really hurting here. So what should we be doing is we should be adopting sort of more this performance-based design framework, which is becoming more popular in codes even. And this recognizes that there's a whole range of earthquake levels. So going from these very, very small events to these very, very big, perhaps even unpredicted events, and asking for different performance under each. So under very small events, you basically want this to be unnoticed by your building. So you want to have zero economic loss. You don't even want people to be scared in their structures. Under middle level earthquakes, you want to think about reducing economic loss, making sure people can stay in their houses and live there, so not everybody needs to move into tent villages or things like that. And also reduce environmental impact from damage. So if you're going to have to tear down all of these structures and rebuild, that's a huge carbon footprint. Then on the very right-hand side, once you have these very, very big earthquakes, that's when your number one goal is to protect the lives of people. And to do this, we focus on different things. So under service level events, maybe our number one priority is building content. Under mid-level events, we start thinking about architectural components, all of these, and your structure in general, we want to protect from significant damage that would cause major repairs. And then under extreme events, we just worry about collapse of the structure. And so that's where this bottom part comes in. So now we're not just thinking about prevent collapse like we did before with the design code, but we're also thinking about accelerations and reducing storage risks. So it seems like a tall order. So we start employing things like high performance structural systems. So one might be isolation, where I'm providing a very flexible layer that goes beneath a building, or it can go at the top of a pier beneath the bridge deck. And this is so flexible that I am putting all of my deformations into that layer and removing the storage drifts basically from the superstructure of the building. I can have dampers, which are going to reduce accelerations and displacements. Rocking, you can sort of think of isolation as removing the shear coupling with the ground, where rocking is reducing the moment coupling of the ground. This is going to be very good for protecting the building, less good for protecting the content. And structural fuses. These are, again, not going to protect the accelerations as much, but they're going to protect your structure so that after a building, maybe you can just replace a single component of the structure instead of having to tear the structure down as a whole. So focusing on isolation, why do we like this? So if that green line is a ground motion response spectra. So the ground motion response spectra, here I have it plotted in log scale in the periods. So if I'm in the short period region, I have large accelerations that I multiply by my mass to get the forces on my structure, and it decreases with larger periods. So if I have a taller building, maybe I'm in this region of my spectra. And so say I have a 3, 4, 5-story building, and maybe I'm out in here in this range of my spectra. 5% damping, even generous for a building. But isolation, because you have such large displacements, if you put dampers down there, things like that, you can really take advantage of damping and get things like 20% damping. So not only am I really increasing my period of an isolated structure because I have a very flexible layer, but I'm also increasing the damping. So these both really help to decrease the forces that my structure is going to see. So now I don't have to design my structure to be as strong, and I can decrease the acceleration. So I'm protecting both the structure and the non-structural components. I'm keeping them from turning to milkshakes. So for example, this is E-Defense test. E-Defense is the largest shake table in the world in Kobe in Japan. It's actually in Miki City, and they tested a hospital. They tested it isolated on the left and fixed based on the right. And one of the hospital rooms was outfitted with all the equipment you can see. So you can see there's lots of hanging equipment, a medical gurney, and a real weight dummy. And so what you'll see is when I play this, that on the right-hand side, you have lots and lots of high frequency shaking in the fixed base building. And you can see my dummy's almost fallen off the gurney. On the right-hand side, you see much slower swaying. Just to run it one more time. Or sorry, on the left-hand side, you see slower swaying, a little bit of sliding because of the long components, but a lot more controlled behavior, more reusable structure after that earthquake. So you're not going to cause as much damage to the hospital facility. It can continue operation, hopefully, after that earthquake. And so here is a measure of the accelerations at the roof of that hospital. So if I have the fixed building, you can see that the accelerations exceeded 2G at the roof of that hospital, whereas isolation brought that underneath half a G. And so it's a big reduction, really helps in the continuity of the service of the hospital. So this all comes into this performance-based design assessment. And that's where we start with things like seismic hazard analysis. And seismic hazard analysis is where you go and you talk to your seismologist, your engineering seismology, hazard maps, and even choosing what ground motions to analyze your structure in. And then this is really where isolation comes in, into the response analysis. We might still have similar ground motions, but what we're trying to do is we're trying to reduce these engineering demand parameters. We're trying to reduce acceleration, and we're trying to reduce story drift by using isolation. Oftentimes with other structures, you can only reduce one or the other, but isolation has this sort of magic that allows you to reduce both at once, and that's what's so exciting about it. So once we reduce these engineering demand parameters, acceleration and story drift, then we decrease the damage on all of the other components in the building. So we reduce the damage on the structure, we reduce the damage on the partition walls, we reduce the damage to maybe all the servers in the building, all of the components in the building. And so when you have reduced damage in all of the components, then you have reduced losses in terms of cost of repair, in terms of downtime and casualties. So just to show you, these are two types of isolation bearings. They're sliding bearings. So you can also do isolation, of course, with rubber bearings. But when we start talking about performance-based design and designing under different levels of hazards, like we had talked about in the beginning, we have those small service level events, the medium design level, and then the big earthquakes, the beyond design or MCE maybe. We start seeing some benefits in different types of isolation systems. So a single friction pendulum bearing, it has a friction coefficient mu, and then afterwards the slope is dependent on the radius of this bearing. So this is just a big steel plate, this is steel, and it slides back and forth in an earthquake. The triple friction pendulum bearing just has multiple of these surfaces stacked together, so that their transition becomes a much smoother behavior. So what you see is under a design basis event, you have very similar behavior between the two. The slopes are very similar. But under a service level event, that small earthquake level, the single friction pendulum has a much sharper transition than the triple friction pendulum. And even now, there's still a lot of development in terms of multi-surface friction pendulums. There's now a quintuple friction pendulum bearing. There's work on how these sliders reach the end of their transition. It's a very ongoing, moving field. So just to compare, let's see what happens at the triple friction pendulum when it's happening on stage one. So stage one is that initial in that gray region of this backbone curve. So you can see that I'm moving really just in those inner sliders. There's a black gasket, black rubber gasket around there. So you can see the movement is not on the outer plates, only on the inner plates. And the rubber gasket just goes with it. And then you can see once I move beyond, I start getting this nice transitioning. Now I'm moving on the inner sliders as well as the outer sliders, but I'm not actually engaging the higher modes by impacting the sides. So that can be shown through here. So you see how this motion goes. First, I move on the inner two sliders. Once I reach the friction coefficient of the bottom, I slide there. Then I'll reach the friction coefficient of the top, and I'm sliding on the outer two sliders. I engage the bottom. I'm sliding on an inner and a top. I engage both the outsides, and I still have some movement in the inner sliders. So that means it's not a hard stop. There's a transition. On the return, I start going on the inner sliders, the bottom. Now I'll start moving on the top as well. And I'll have a large displacement there until I start engaging the rims again. And I'll start having a hardening effect as I engage the rims. And one thing to note is that these are all hysteretic elements. And because of that, even though I'm going to return to zero displacement, the displacement on all of these inner components is not necessarily going to return to zero, which means I'm going to still have some offset vertically in my bearing after I go through a loop. So this is the forced displacement loop of that bearing. So looking at a case study, this is just a cute little 3-story building. It's got a fixed base period. That's the period without the isolation layer of 0.6 seconds. And I've designed 2 bearings for this system. One is single friction pendulum bearings, SFP, and triple friction pendulum bearings, TFP. And we've designed them so that at their desired displacement capacity, 30 centimeters, they both have the exact same effective period, and the effective period is measured based on going from the zero displacement, zero force point, to the maximum displacement, maximum force point. So if you could draw a line from here out to here, that is your effective stiffness from which we find the effective period. The effective damping is the same, which means that the area inside both of these loops is exactly the same. We're running them under 2 levels of ground motion. So one is that service level event, 50% 50 years. The other one is the design level event, and that's 10% probably in 50 years. So looking first at drifts, this is just a cumulative distribution function. So the drifts in my fixed base building under my design level event, the mean was roughly 1.5% drift, whereas my single friction pendulum and my triple friction pendulum brought this way, way down to less than 0.25% drift. So this is impressive because we start seeing damage to partition walls at about 0.5% drift. So we've really saved a lot of damage to partition walls, which can be very costly after an earthquake there. And we know we start having major damage to especially less ductile systems out around 1.5%, 2% drift. So we're really have benefited both the non-structural content in terms of the partitions as well as the structure. Then we look at accelerations, and I'm looking at the service level roof spectra and the design-based earthquake roof spectra. So these are the accelerations for every different frequency measured at the roof, and this is the acceleration. And so black is your fixed base building, and you can see that both the single friction pendulum and the triple friction pendulum have reduced this quite a bit, and that's also true for the DBE. So here we see that basically any isolation system, single friction pendulum, triple friction pendulum, any isolation system is going to do a good job reducing your accelerations from a fixed base building. But especially in that service level event, that's where the benefit of the triple friction pendulum having a smoother transition curve in the beginning really starts to shine. So you're getting these multiple performance objectives over different levels of earthquakes. So we've talked a lot about isolation working very well under under small levels of earthquakes. And this is very, very well known. So whether you choose a rubber isolation bearing, a friction pendulum bearing, we know that it's going to work well under typical hazard levels. But what about in an extreme event? So a really big earthquake, how should we best design these buildings? So this is going to have to answer two questions. How do isolated buildings fail? And what kind of safety factor is in their design? And so we talk a lot about capacity design for other structural systems. So for example, in a moment frame, we know that we like to have strong columns, weak beams, and we like to have plastic hinges forming at the ends of my beams. But what happens in an isolated building? Should the weak link be yielding in your superstructure, or should the weak link be failure in your isolation layer? Now, ideally, neither happens, but if we don't know what happens, we don't know what the safety factor is. So, do we allow superstructure yielding? And if we do, at what displacement level? And what level do we need to design the bearings for? And so ASCE, the US code 716, says the answer for both of these is MCE. For standard buildings, fixed-base buildings, so if I'm going to design a 5-story moment frame, ASCE 7 designs for the DBE. But for isolated structures, it says, okay, because these are higher performance structures, it needs to design for an MCE. And that's a good start. So why don't we want to allow yielding? Because if we look at this graph, the black is my response spectrum. And say my building starts with this yellow period, or this period here. And as my building yields, so say it's a typical fixed-base moment frame, as it yields, my period will get longer because my building will be more flexible. And so my accelerations are basically, my demands are going to go down the hill as I have yielding. Whereas the blue is sort of a cartoon of what the spectra looks like on top of the isolation system. So if I start with my building here, because it's filtered by the isolation system whose period is out here, as I yield, the forces almost start to increase in that structure, which is not beneficial for the post-yield behavior of that isolated superstructure. The other idea is, if I have yielding in my structure, which is the yellow, at some sort of or DBE or before MCE level displacement of the isolator, so the forces are about the same, then I'm going to start having equal displacements almost. You can think of it as a spring in series in my isolator and my superstructure. So there's some very strong arguments against allowing your superstructure to yield, but less thought about what should be your required bearing displacements. So we did a study, and it was looking at the capacity design for isolated buildings, and we looked at a concentrically braced frame and a moment frame. Both were designed in steel. And we wanted to look at the effective design methodology, including bearing displacement and superstructure strength. And we wanted to look at the effect of the bearing rooms. So, for example, in North America, we usually have these restraining rims, but sometimes in Europe, sometimes in Japan, you see these rims removed. So here our thought is, we can't let the bearing just fall off the edge. And here the thought is, we can't let the bearing impact. So they're both good lines of inquiry. So to do this, we looked at triple friction pendulum bearings, and that's just because they simply have a little bit easier behavior to model in terms of extreme events. And so you can see the double friction pendulum bearing just has a top and bottom concave plate. It looks a lot like a single friction pendulum bearing in terms of its displacement and force loop. we ran some experiments on these bearings. And so this was a shake table, just a small little shake table, some concrete masses on top of two bearings, and then these frames here. These frames helped keep those masses in line as we shook the table. And these were their isolation bearings, and we cut the sides off so we could see very, very well what was happening inside. So you can see here's my isolation bearing, my top and bottom plate. I've got the inner slider, and I have the load cell below. We looked at 4 different types of isolation bearings. We looked at ones that had absolutely no rim. So you can see this is the side detail. There's no rim here. Then we looked at 2 that had rims. One had a thin rim, 5 millimeters thick. The other one had a thick rim, 10 millimeters thick. And then the other one was this sort of special detail to Japan, where the rim was bolted all the way around the bearing. So basically the bottom plate was milled and then a separate rim was bolted around. So we ran these under Kobe ground motions, and we ran this because it has a big pulse in there. And so that pulse has a long period in terms of earthquakes. So you can see the period of this pulse is maybe roughly a second or and a half. So, and isolation systems, they have a very long period. So pulse-like ground motions can be very detrimental to an isolation system. It can really cause large displacements for them. So we tested lots and lots of configurations, but the hard thing was we didn't want to damage the bearings before we tested them under really large events. So we had to think a lot about the order in which we ran our ground motions. And so this is a test of the no rim bearing. So these rims here underneath there have no rims, and this was 150% of that Kobe ground motion record. And so if you saw right there, it almost really goes off to the edge on the left, very close to the limit of these bearings. And so we have high-speed cameras looking at the behavior of these bearings. And so you can see we're sliding back and forth under ground motions. And we're going to have a very large excursion out to the left. It almost touches down, but because of that inertial mass and the weights above, it actually returns to zero, and these isolation bearings, even though they almost failed, are still operational for the next earthquake. So this was 150% of the JR Takatory motion. And so you're going to see this, they actually just return almost to zero. There's a little bit of offset, and that's something to think about. Under a very large earthquake, are you going to have to drag your building back a couple centimeters? But this is 155. So last was 150. This is 155. And you're going to see very, very large displacements and basically a failed isolator. And so we didn't foresee that. Oh, you can see again, almost fails completely. It sheared off the layers of the slider. And that was really just luck that it landed on that bolt. So you can't control that. That's probably a detail that's not going to happen. So you have to imagine that perhaps your building has just sort of jumped down by a couple feet if this behavior happened in your building. So we were very lucky that it landed on that bolt. This is, instead of having no rims, which I saw before, what happens if I have thick rims? And so very different behavior and rocking. So you can see as that impacts back and forth, the superstructure has some rocking in it because it has large force at the base. Lots of uplift there too. Very large forces that would be transmitted to your superstructure. So just show you, this is 155 where the bearings with no rims did fail, right? And so I'm going to have a little bit of uplift. You can see it on the right. It starts causing this bouncing, these vertical accelerations in my superstructure. You can really see it here. And so here's this really big question, because the flat sliders, they failed under this motion, 155% takatory. And these bearings, they didn't. And in fact, you could continue running earthquake ground motions on these bearings. But the forces that you have input into your superstructure have maybe caused damage to your superstructure and have certainly caused damage to your non-structural components. So if you look at the hysteretic behavior from these two ground motions, this is just sort of what it looks like. I'd like you to notice that my scales are completely different. That's important to notice. So here my shear force for the no rim bearing goes from 20 kilonewtons to 15, whereas for the thick rim, it goes from -100 to 60. So completely different scales. But you can see that the no rim bearing controls the forces that are transmitted through your isolation system, whereas the thick ones have humongous spikes in the forces that come through. And if you see all of these really bumpy motions, that's because of the vertical accelerations. And shear force in these bearings is the friction coefficient times the normal force. So if I have vertical accelerations, then my shear force is going to fluctuate like that. So we still don't really have an idea of which kind of rim is better. Again, you can see that, that as I go on beyond, my displacement capacity is around point here in the middle, and as I keep getting larger and larger isolation or ground motions, my acceleration just increases really huge as soon as I start having impact. Whereas when I have no rim, eventually my slider just drops. But the bearings that did have rims, they never failed. We were a little too scared to run them past 155% takatory in the lab. And you can see these are the aftershock motions. So basically, we ran 70% of the ground motion after we ran 155% of it. And so you can see they have actually very nice behavior, even though we've had very large events in those motions, or on those isolators. Just what we have is some damage, which has caused an increase in friction, which is why the black lines are thicker than the red lines. We also looked at the damage of the bearing. So for example, if you look at the no rim, you can see that this is the Teflon surface, and it's basically been sheared off here under the large events. The bolted rim, because there's sort of a lip here, that lip really damaged the slider and it had a huge sort of gouge in it. If I had a thin rim, you can see the yielding in the plates, and the thick rim, you even see a little bit of yielding in those plates as well. And so you can see this sort of this patch here. It looks like scratching, but it's more like a polishing. So these Teflon surfaces sort of wear off. It actually gives it very good repeatable behavior. So that's not actually damage to the surface. So we have then models that we do to try to predict these behavior. So we could model them in Abacus and finite element software, and you can see really I'm getting some yielding in the rims and then uplift. That uplift is because this is a very light superstructure that we modeled here, but that's very, very computationally expensive. So we have also rigid body models that we can do, say in MATLAB, that predict the same behavior, except they can't do the yielding in the rims. So I'm going to have impact here on the left, and then that exact same behavior I saw on the right. And because I'm getting the same behavior and it takes much less time to run, I'm going to use these in my analysis to try to start thinking about which systems are better for isolation. We also have the flat rim model using the same methods, and you can see that they come out very far. And oh, I think I skipped the good part. Anyways, if you come out here, maybe not. You can even get motion all the way out on the edges of these rims. And so you can see this is our flat rim model on the left. Coming down is with time. And this is our experimental high-speed data on the right, coming down with time. And you can see this behavior here where the edge of the puck comes off the sliding surface. We're getting that in our model as well. And you can even see that because of this flat rim on the side, it sort of gets caught on the bearing. And what is typically really symmetric behavior becomes unsymmetric behavior sort of halfway down. And we see that also in our analysis or our high-speed data. So we use these models to look at what kind of ideas for capacity design of buildings we should think about. So we have the these are opposite. We have the concentrically braced frame and the moment frame. And, and we have three design methodologies. So the first one is the baseline design. And that's where our isolators are designed for an MCE, so a large event with accidental torsion, and the superstructure design is for MC forces with a small R factor. And this baseline design is based on the current ASCE standards. So this is ASCE 716. Then we have a stronger superstructure design. So maybe I don't want to allow yielding in my superstructure for the reasons that I talked about before. So we increased the forces to design the superstructure by 120% of the maximum force at the bearing. So what does the bearing actually get? Let's go even bigger to account for some impact. And then we have the larger bearings. So the bearings, we kept the same superstructure from number one, and instead of increasing the strength of the superstructure, we increased the displacement capacity of the bearings, and we increased it by 50%, which was, if you looked at our record set, it was close to the mean plus one standard deviation of the demands from the record set. And we used the FEMA P695 pulse light ground motion suites. FEMA P695 is a pre-standard for understanding collapse and R factors that are assigned to different structural systems. And so to do that, you need to run an incremental dynamic analysis per FEMA P695. And so an incremental dynamic analysis, each one of these lines on the left is a ground motion, and on the left-hand side, you can see I'm incrementally increasing the strength of that ground motion. So I'm basically just turning that ground motion up and up and up and up and up. And each time I turn it up, I actually do an analysis of my structure and record some kind of value, perhaps maximum story drift ratio, perhaps something else. And we look at the performance from each one of these lines, which is a different ground motion. And we see when each ground motion causes failure or collapse. And you end up with this collapse probability from that suite of ground motions. So again, we use the FEMA P695 suite of ground motions. So these are the ground motions. They were scaled to the period of the isolation system. And then all of these ground motions were incrementally increased. So this is our IDA incremental dynamic analysis responses for all of my motions. On the top row, I have my moment resisting frames. On the bottom row, I have my concentrically braced frames. And so on the left-hand side, what I'm showing is what happens if you do that code-based design. And that code-based design, what happens is, so for example, I have an IMR, impact margin ratio, and a CMR, collapse margin ratio. So at 120% of this ground motion, I have impact with the rims. So you can see I have very low drifts, then I have impact with the rims. My drifts increase quite a bit, And then as I turn up the ground motion, 130, I have larger drifts, but I still have impact, but I don't have failure. And at 140, I now have failure. Okay, and you can see that my drifts are largest at my first floor, smallest at my third floor. So once I impact, I can still go a little bit larger with that CMR to get before I have collapse. When I start having a stronger frame, so I've kept the bearings, but now I have a stronger frame, my impact happens a little bit sooner than the code compliant. And that's because my superstructure is stiffer, which means more of the displacements are pushed into the isolation layer. So the impact happens sooner, but my collapse happens later. So there's this really big time zone in terms of magnitudes of my earthquake that are in between impact and collapse. Now, maybe that's good because I've pushed collapse to be later, but remember in all of these ground motion intensities here, I have impact, which means I'm pushing really large accelerations into my structure, even though it's isolated. Then I have larger bearing design, and you can see both my impact margin and my collapse margin are pushed way out to the right. So much, much larger collapse margin ratio. That's a good thing. And the difference between impact and collapse is really small. And that's because I don't have a lot of extra strength in my superstructure. So as soon as I get out to these forces, very quickly afterwards, I'm reaching collapse. But again, I'm not certain that that's a bad thing. I think because we're trying to protect our content as well, that's actually quite good. For concentrically braced frames, we have a different behavior. Whereas we see with this stronger frame design with moment frames, I really am seeing a big difference with impact and collapse margin ratio. You don't see that with concentrically braced frames. So you can see as soon as you hit with concentrically braced frames, your drifts in your first floor go way up. I have yielding, buckling in my braces, poor behavior in my first floor, and I'm reaching collapse very quickly afterwards. The only thing that really helps this concentrically braced frame is having these larger bearings. So you can see with the larger bearings, I still have very low drift ratio until I have impact and then collapse. So what causes failure? For the moment resisting frames, for this code compliant design, failure is partially due to yielding of the superstructure. So even though we're talking about an isolated building and it's code compliant, under large earthquakes, the failure is coming from yielding in the superstructure. And then some of the ground motions are coming from a combination of the bearings failing and the superstructure yielding. Then if I start having a stronger frame design, some of the ground motions are actually coming from my bearings failing exclusively. But if I go to my larger system design, most of it is from yielding. From CBS, all instances of failure are coming from excessive superstructure drifts. So that's concerning. As soon as we have impact with the concentrically braced frame, we have large superstructure drifts leading to failure. So we're looking at the probability of failure using all of those incremental dynamic analyses. And we can see that for the moment resisting frame, we draw these nice lines of my fragility function, my collapse fragility, which is just a cumulative distribution function. And my MCE level is, my scale factor on the bottom is so that MCE level is 1. And in the US design code for a typical building, not a hospital, not a 911 center, but a typical building like an office building, your collapse probability for those buildings is 10%. So you can see that your code compliant design, you're getting underneath your collapse probability. I would argue that for an isolated building, since you've put more effort in and you are spending maybe a little bit more money, maybe 2% more money, you should probably be hoping for an even smaller probability of collapse. You can see with the stronger frame design, your collapse probability is 5%, but again, you're probably putting in a lot of accelerations even before that. And for your larger bearing design, this gives you the best behavior, and that's that 3% collapse probability. So we've really decreased it. And so remember that even the collapse probability is 10%, the probability of impact is significantly larger. And that probability of impact, that's what's going to really drive up the damage to your non-structural and perhaps even structural system components. The concentrically braced frame is more concerning. So you can see the baseline, and then a little bit different as the code compliant, has a larger probability of collapse, so around 10 to 15%. The stronger frame design doesn't do any better, 15%. And the larger bearing design is the only thing that can decrease that collapse probability to below 10%. So we need to really think about making larger bearings than what is just code compliant level. Okay, and so we've been just talking about bearings with rims. So what if I have bearings with or without rims? And you have to remember when you're thinking about this, you can have bearings with or without rims, but eventually you have a moat around your building too. So if you're going to start using these flat rims, you have to imagine that your moat is going to be even further away. So looking at the same incremental dynamic analysis, on the left-hand side, I have moment frames. On the right-hand side, I have concentrically braced frames. On the top, I have rigid rims. And on the bottom, I have flat rims. And you can see for moment frames, as soon as I have an impact, I start having very large drifts until I get to collapse. If I remove the rims from the bearings, this impact is not actually impact, which means that my drifts stay pretty flat. They increase very slowly until I have collapse. And you can see it's a little bit higher here. And for my concentrically braced frames, as soon as I have impact, I have very large drifts and leading to collapse. But if I have a concentrically braced frame with flat rims, my drifts are fairly constant because it's such a stiff system until I have. So the effect for moment frames is moderate, going from a collapse margin ratio of 1.4 to 1.5. But I would say that in terms of decreasing accelerations for your non-structural components is very beneficial. And then the CBFs, you can see a big benefit in collapse margin ratio, 1.2 to 1.4, plus decreasing accelerations. And so you can see the black line is my rigid rim bearings and the red line is my flat rim bearings, and I'm pushing that fragility curve and making the probability of collapse at a scale factor of 1 smaller by getting rid of the rims. But really what this is doing is it's extending the displacement capacity. So in general, isolation we know provides excellent performance as long as the displacement limits are not reached. And I just want to keep repeating that, as long as the displacement limits are not reached. CBFs perform better under small earthquakes. We know that because they're very, very stiff. And that means that the isolation, the displacement is all in the isolation layer. So then I can really decrease my accelerations. So while CBFs perform better in smaller earthquakes, they have a larger probability of collapse than MRFs. And that actually really boils down to the stiffness of the system. When you have a really stiff system and you subject it to that pulse, it's going to have large ductility demands, and that's what's driving that higher probability of collapse. So when I have a rigid rim, only MRFs, moment resisting frames, are benefiting from strengthening, while the CBFs are not benefiting. And only increasing the displacement limit decreases the collapse probability for CBFs. And when I have flat rims, I had significantly better performance for CBFs, smaller improvements for flexible MRFs. But even though the smaller improvement in terms of collapse probability, I've probably really saved myself money in terms of non-structural components. I've also probably increased the probability of being operational after an earthquake. But I really want to drive home this one point. Isolation is fantastic, but if you do not make sure your bearings have sufficient capacity for displacement, you're not doing yourself a service in the long run. So I would suggest even going beyond what you would call MCE level displacement, large earthquakes or so on, making sure you have low probabilities of reaching those displacement capacities. And that's not just in terms of designing the isolators to be big, but in terms of accommodating moat sizes, making sure that all your moats are clean so that you don't have your facility services storing places or storing equipment so that your isolators don't reach their capacity. I've seen buildings where people put isolators in and then maybe the facility services built little rooms around the isolators, which meant that they couldn't actually function. So you have to make sure that your isolation system is protected and ensure that it's going to operate well under these large earthquakes in order to see this benefit in general. So thank you. I also want to thank Takanaka Corporation, that's their logo there. So they're in Japan and they were working with us on all of these projects and they were very helpful.
Hi, Dr. Becker. Thank you very much. It was a very enlightening presentation. I had too many notes and I have too many questions for you, but I think we don't have the time for that. I want to first know if anyone online has a question for Dr. Becker, so you can type it on the chat feature that we have with the GoToMeeting platform, so you can just place type it and I will read it. I have a question for you, Dr. Becker. What's the material for the inner sliders so that when the upper part of the seismic bearing goes all the way as far as it can go and it just doesn't break? What type of material is it, just to resist the amount of shearing that is created over there?
So in these extreme ones, so all of these bearings are made out of steel. So they're all just stainless steel bearings, and you can see we have just yielding in that rim instead of any fracture. And that's simply it. These ones that are milled out of one piece, so all of these bearings, the no rim, the thin rim, the thick rim, they take one piece of steel and they mill it down. So this is a continuous piece of steel, although sometimes these sliding surfaces are sort of added on afterwards. These bolted rims didn't perform quite as well, and that's because the rim was not connected. Yeah, when you have sliding bearings like the triple friction pendulum bearing though, what happens is when you hit these outer rims, you still have some displacement capacity on the inner sliders. So the force is not very large when you hit those outer rims because I'm just going to start sliding on a different surface. So it's almost like a breakaway mechanism or something.
All right, thank you very much. Impressive. Dr. Becker, is there any requirement for the surface finish of those metal vases? Like, does it have to be rough up to certain amount of micro, I don't know, like with the units of surface roughness, or does it have to be completely mirror polished, and the surface, the force is created just by the vertical component and whatever friction that we have between these two surfaces?
Yes, so these sliding surfaces, the dishes, are usually a polished stainless steel. So those should be as smooth as possible. And then the friction surface, it's just caused by your normal force, so your axial load, and then usually on the sliders themselves, so on the bottom of this little silver puck or on all of these surfaces here, we have liners that are adhered to the steel, and these are usually like a carbon or Teflon surface, and they're proprietary to the company. I will say that it is important that when you have friction bearings, that they're of high quality. So it should come from a reputable manufacturer. They should be tested in a laboratory to make sure that they're durable, that they're going to have the desired performance under lots of ground motions.
All right, thank you very much. I think we have a question online, Dr. Becker. Let me read it for you. Okay, this is Dr. I think you met him, Jesus.
Yes.
Villalba. I think that's actually how I got to contact you in the first place. He says, how do you include reliability for mechanical behavior of the material?
So that's a very...
It says inside of the behavior calculation of these structures. Well, that was a long question.
So basically what is generally done is there will be, so these friction coefficients for these surfaces, they depend on velocity, they depend on pressure, they depend on temperature. So for example, say this bearing is going to go into a bridge, right? You're going to have very different temperatures on the bearing from winter to summer. And also when you start sliding on these bearings, the temperature goes up very, very quickly from the friction. So when you're designing these bearings, what you need to do is analyze your structures, assuming upper and lower bounds of your friction coefficients. And so typically you'll work with a manufacturer to understand what the upper and lower bounds of all of your friction would be, and you conduct analysis accordingly. And so there's even some code guidelines on this in chapter 17 of ASC 716 on suggestions for the bounding analyses you would do.
Okay, thank you very much. One last question from our faculty members, and there's one question of a master's student. The question goes as this: Have you attempted any topological optimization of the geometry of the friction pendulum? You know, applying topology optimization. I think that's what I tried to mean.
In terms of topology optimization, we have not. We've done a little bit of optimization of which the radius is all the surfaces. So the radius controls every single slope in here, and it will control how you translate, or transfer between them. And so we've done some optimization for different systems, just considering that. And what is tricky is when you start thinking about optimization, including not allowing large displacements, plus controlling accelerations and displacements under smaller earthquakes. And so we have a couple of works on that. If you're interested, feel free to email me. My email is, I should write this. And put it right here, and I'm sure you can get it. Maybe you could also get it from the moderator, right? So you can get my email at Berkeley. So I'd be happy to share that. We haven't done anything in terms of changing the surfaces of the bearing are, except sometimes we think about changing the transition from the sliding surface to the rim. So if that's smoother, you want this to be a nice sphere. Otherwise, you're not going to have even bearing on these sliding components. So you don't want just portions of these sliding components sitting on the bearings, because then you're going to start having wear over the lifetime.
Right. Well, Dr. Becker, I don't know if you have time for one last question. This one comes from a master's student. He wants to know, once the structure gets, once the pendulum hits the outer ring, and we saw that vertical displacement that becomes a vertical acceleration. Right. What happens to the structure? Do we have to increase our design in terms of vertical shearing, vertical actual courses and so on and so forth, just to make sure that in case I am completely sure you don't want that type of service level when you are having your surface, I'm sorry, your base isolation. But what if it happens? I mean, okay, let's build the base. This ground motion was so strong, it just hit. Do I have to prepare myself for a certain level of acceleration so we can have like a little extra design in it just in case?
I guess my advice is, if you were going to spend a little extra money on a design, I wouldn't spend it on adding more strength to your superstructure. If you had just that little extra penny to spend on your design, I would spend it on making the displacement capacity of these bearings even bigger and allowing it to displace more. Because as soon as you start having that impact, you will have high accelerations vertically, and they're probably higher than if you just did a little extra vertical design. What is nice though is that impact forces generally sort of dissipate after the first floor. So even though you might get large yielding in the first floor, which could potentially cause collapse, usually the yielding isn't going to increase all the way up your building. But again, if you have that extra penny, just keep your system from impacting. That's what I would say.
All right, thank you so much. Well, everyone, thanks for being online, and for the students that were here with us, thank you very much. We understand you might be busy, Dr. Becker, and also here the room is going to be busy very soon. Thank you very much for the presentation. I want to ask you publicly if it's okay for us faculty members to contact you, because we have a lot of ideas with your presentation, the things we're doing locally. We also would like to, even in the future, invite you to come to Colombia to see our new research facilities. They're just brand new. We had a recent 100 million investment on this. Yes, but we need people to guide us what to do, and we need people and professionals and professors with the expertise that you have. And of course, we'll be glad to invite you to come over to Javeriana University and repeat what you just did in here virtually, but this time with us here in Bogota.
Well, I look forward to talking to you and all of your faculty future, and thinking about future collaborations. It's very exciting.
Well, thank you very much once more, Dr. Becker. Have a good day, and everyone, thanks so much for attending, and bye-bye.
Bye.